Yes.
Hello, everybody. Welcome to another edition of the String Seminars. Today, we're very happy to have Sunil Mukhi. He's going to tell us about the classification of a certain class of rational CFTs.
Thank you very much. It's a real pleasure to be here. So I'm going to talk about this, about work from a few months ago on the classification of all rational conformal field theories in some range of central charge, but having a single primary field, a single non-trivial primary or a single critical exponent. I'll explain as I go along. So the main paper is this one with Brandon Rayhaun. Now it's now a postdoc at Stony Brook. And as you can see, it has the same title. There are also related works from last year with Arpit and Chethan. Chethan is at IISER, Arpit is in Durham. And I may mention the second one of these towards the end of my talk. I'm focusing on this because there's a very precise thing that I think I can hopefully explain in the available time. There's quite a lot of background. So these are papers with master's students, mostly with master's students at IISER Pune. And there's also much older background of work that I did with Samir Mathur and Ashok in 1988-89. So I'll actually, because probably a lot of people are not familiar with this approach, I'll actually start by summarizing some of these papers and then get to the more recent results. So by way of introduction, 2D CFT is something that has been intensely studied for nearly 4 decades, starting with the pioneering work of these people, BPZ in 1984. And 2D CFT can be defined as a special class of 2D field theories, having infinitely many symmetry generators, Ln and Ln bar, so 2 infinite sets, each of which independently satisfies a Virasoro algebra with a central term proportional to C. So it takes a fixed real value and it's called the central charge. And for a unitary CFT, it's necessary, but not sufficient, that C should be positive. So let me start by giving a few physics motivations for 2D CFT. They describe critical systems in statistical physics. This was the oldest motivation. But then it got a huge impetus because we understood that they described the world sheet of relativistic strings. You can use them, you can use 2D CFT in ADS3 CFT2, obviously. So I should have said here that it's the rational CFT particularly give rise to a quantum or stringy version of ADS3 CFT2. They are relevant for the study of anyons and the fractional quantum Hall effect, and to something a little speculative called topological quantum computing. And there are probably also other applications I haven't listed. On the mathematics side, there are also motivations. So CFT, what we call rational CFT, precisely translates to a concept called vertex operator algebra or strongly rational vertex operator algebra in mathematics. These are related to modular tensor categories, which I'll briefly discuss because I'll need them, and to the concept of vector valued modular forms, which also I'll discuss, and to modules for sporadic discrete groups. This I won't discuss, but it's one of the mathematics interests of CFT. Okay, now CFTs very often have additional symmetries beyond the Virasoro algebra. So Virasoro is like the minimal algebra you need to have. And whatever the full symmetry algebra might be goes by the name of chiral algebra. So when I say chiral algebra, it will be whatever happens to be the complete infinite dimensional symmetry algebra of the theory. Now there's one class of chiral algebras that arise very commonly, and they arise for CFTs which have a global symmetry under some Lie algebra G. So what happens is that if there's a global symmetry and also a conformal symmetry, then these two sort of combine and give you a Kac-Moody algebra, which has infinitely many generators J and A, where A is a Lie algebra valued index and N again takes all positive and negative integer values. So this is a Kac-Moody algebra and it has its own central extension K, which is called the level. Now, there are CFTs which contain all integrable representations of a Kac-Moody algebra. That's a finite set for any given level K. And those are called Wessumino-Witten or affine theories. And in such theories, it's always the case that even the Virasoro generators are not fundamental, but rather composite and made out of the Kac-Moody currents as a normal ordered bilinear. But it can also be true in more general non-affine theories, which do have a Kac-Moody algebra, that the stress tensor is still made up of that Kac-Moody algebra in this way. And then we call the theory pure Sugawara, because this is called the Sugawara construction. We also say that the Kac-Moody algebra is complete. That means that there are no pieces in the stress tensor which don't come from the Kac-Moody algebra of the theory. And generically, there can be, and we'll see theories which actually have that feature, that parts of the stress tensor don't come from Kac-Moody algebras. So this is all just background. One or two more slides of background, and then I can get down to the talk. The Hilbert space of 2D CFT is graded by conformal dimensions, which are the eigenvalues of L0 and L0 bar. It decomposes into representations or modules over highest weight states called primaries. And so the number of primaries is the same as the number of modules. And the primaries, by definition, satisfy that the modes of the full chiral algebra, whatever it might be, they annihilate the primary for all positive indices n. The conformal dimensions of a primary are denoted hi and hi bar, and there's a distinguished primary called the vacuum, which has h0 equals h0 bar equals 0. Now, once we have got these highest weight states, then all the remaining states in the theory are descendants, and the descendants are obtained by taking the primary and sort of exciting it, taking it to what you might call the analog of an excited state by the negative or creation modes of the chiral algebra, both the holomorphic and the anti-holomorphic modes. So that's the structure of all states in a CFT. And if the number n of primaries, actually it should be called the number p of primaries, is finite, then we have what's called a rational conformal field theory, and it has very special properties, and we'll explore those. Now, it turns out that the number of primaries being finite is equivalent to the statement that the central charge C and all conformal dimensions hi are rational numbers. This is a theorem that was proved by Anderson and Moore in 1988. Yes, please. Yes. Yes. No, so I think those are called quasi-rational. So, okay. Good. No, I think not actually, because, for example, if you take a free boson at a radius which is r squared, where r squared is irrational, then of course C is still rational, but H's are not rational. And I think you still have finitely many conformal blocks for the 4-point function, because the fusion of any two primaries gives you a finite or even just one. Yeah. So I think in quasi-rational theories, it might be that C is rational, but I don't think H has to be. Okay. I think it is if and only if. I think that's the statement is if and only if, that Anderson-Moore statement, that if you... Yeah, I think it's a strong statement. I actually should check. Yeah, so one direction, let's see, which direction? If the number of primaries is finite, then C and H are rational. That's reasonable. But I have to think more about this. But somehow, I'm not sure about the other way. Something to, yeah, I'll check again. Okay, yeah. Yeah. That has finite number of primaries, and it has C and H rational. So at any integer value of r squared, any rational value of r squared, the same is true. And one thing I should emphasize here, that the number that I was very careful about the definition of primaries. These are not Virasoro primaries. So there's an entire field of conformal bootstrap applied to 2D CFT at generic, large, irrational, or random, arbitrary values of central charges. And there very often the Virasoro primary is given a privileged role. While when studying, and that's partly because we expect those theories don't have any enhanced chiral algebra. Okay, so the generic theories you want to consider for ADS CFT are theories which have only Virasoro symmetry, and they're as generic as they can be. However, when you have actually finite number of primaries, the theories typically do have enhanced symmetries, or I think always have enhanced symmetries. And so it makes sense to define the primary with respect to the full algebra, not the Virasoro algebra. After all, if we did define only with respect to Virasoro algebra, then we could never have a finite number except for C less than 1, and that's already classified and there'd be nothing to talk about. So here we are talking about theories with a finite number of primaries under the full algebra. Just want to emphasize that. Okay, the partition function of a 2D CFT is defined by this sort of trace. This is well known. It basically generalizes the usual partition function by complexifying the beta parameter, inverse temperature, and brings up and introduces these shifts and also a complex parameter tau. And in the path integral language, this is computed by a path integral on a torus whose modular parameter is that tau. And in rational CFT, Z, which is written like this, can be further decomposed into a finite sum of bilinears where each of these chi's is holomorphic in Q, and it's just the trace restricted to the descendants of a particular primary, and that to the descendants only the holomorphic descendants, and chi bar likewise for the anti-holomorphic descendants. Okay, so this is the form of the partition function in a rational CFT, and the rest of this talk will be focused on finding characters chi, which can give us partition functions of rational CFT. One comment here, which is almost obvious, is that these characters are holomorphic in the interior of moduli space because they are basically some power of Q, which is fractional, times an integral power series, because L0 has integral eigenvalues apart from the fractional dimension of the primary. All the descendants are spaced in integers. But these characters diverge as tau goes to I infinity, which is Q going to 0, and that's because of the fractional C and H appearing here. So they have a holomorphy property, and that's extremely useful. Now, one small subtlety, but it's sort of important, is that the number of independent characters, so in this formula, you see there's a number n. So these indices go from 0 to n minus 1, which is n values. That number n is the number of independent characters, but in general, it's less than or equal to the number of independent primaries in the theory. And in other words, multiple primaries could have the same character. And this most commonly arises when you have symmetries like complex conjugation. So you have a primary that's complex. For example, it can be the n of SUN. Then we know that the n representation is complex. It's the fundamental, and its complex conjugate is n bar, the anti-fundamental. But actually, the character for the n and the n bar are exactly the same. So in this case, you have two primaries, both with the same character. And yeah, so this can happen. So we'll sometimes use this notation that a CFT with P distinct primaries is labeled as a PCFT. So P is the number of primaries always. Yeah. Yes, good. So good. Thank you. So if so exactly right. So if we consider what the most general characters which have what we call chemical potentials or flavors or something, then actually these get distinguished by turning on those flavors. But it's not appropriate to turn on flavors in this sort of discussion because we don't know in advance what the Kac-Moody algebra is, and the flavors are typically associated with the Cartan subalgebra of that algebra. So you can't really discuss different CFTs in the same breath if they all have their different chemical potentials turned on. And to discuss those, you would then already know what the Kac-Moody algebra is, and so you wouldn't be doing whatever I'm doing here. So we consider, yeah, there's some word for it also, I don't know, reduced or specialized characters or something. That it's because of that, you're completely right, that phi and phi bar end up having the same character. There are also cases where as many as 3 different primaries or more than 3 have the same character due to some symmetry of the theory. Okay, yes. Yeah, probably. Yes. I mean, okay, good. Yes, indeed it does. So the 2 most common cases are complex conjugation, which is a reflection of the Dynkin diagram, and triality in the case of SO8, which is a 3-fold rotation of the Dynkin diagram. So probably that's what it is. Yes. Yes. Okay. Now, the partition function of a CFT in general is required to be modular invariant, and this follows from the assumption that the trace as which we use to define the partition function is calculable as a path integral over a torus. And modular transformations are basically global diffeomorphisms of the torus. And so if I take the parameter q, which is e to the 2 pi I tau, and replace tau by this thing, a tau plus b over c tau plus d, to get a new quantity q gamma, then z evaluated on q gamma should be the same as z evaluated on q, because we can't, in doing a path integral, we can't tell which description of the torus we are working with, whether through q or q gamma, and therefore the answer must come out the same. Now, the thing is, z is modular invariant, so that's a very strong constraint. And so you could ask a question like, how many functions of q and q bar can I find just by abstractly requiring modular invariance on them? The problem is these are not holomorphic because they depend on both q and q bar, and then it's not so easy to answer that question. Okay. However, what you can do is transfer the question to the characters. So what does modular invariance of z tell you for the characters whose bilinears make up z? And the answer is that the characters are vector valued modular functions of VVMF of weight 0. And this, I think you can see, okay, first let me say what that means. VVMF of weight 0 is a set of functions, chi I of q, such that chi I, when I transform q to q gamma by a modular transformation, come back to themselves in a linear combination with a matrix rho ij of that transformation gamma. And clearly from this, rho is a representation of SL2Z. Okay, and it's an n-dimensional representation when there are n characters. And now if rho dagger rho is 1, then this transformation clearly implies that the partition function is modular invariant, and you can argue it both ways. So for the partition function to be modular invariant, this is the most general transformation that the characters can undergo. Now, this is a better situation to be in because unlike Z, chi's are holomorphic in Q. And so now if we are trying to classify chi's rather than Z's, then at least we have the fact that they are holomorphic and also covariant under SL2Z. So, yeah, please. Yes, and that will be enough for my purposes in this talk, because I'm really going to consider such small numbers of primaries that there aren't any non-diagonal modular invariants. Yeah, otherwise it is rho dagger m rho equals 1 if m is the matrix. Yeah. Sorry? Is m, yeah, correct, is m. That's right. Okay. Now, rho is called the modular representation of the characters, and this will come up as we go along a few times. Good. So now we may take one of two strategies to classify all rational conformal field theories. One is pick a chiral algebra and classify all its representations. This is essentially what BPZ did by saying, let's pick the Virasoro algebra and assume there isn't any other. And I classify all theories where there are a finite number of primaries and we get the BPZ minimal models. Knizhnik and Zamolodchikov generalized this very soon thereafter to the Katz-Moody case, to the Wessumino-Witten models. And both these papers had very beautiful results. But there's a second approach, and this is the approach I'll be talking about. And I'll explain why this is also interesting, or in some ways also more useful. Classify all vector-valued modular forms of a given dimension, which means a given number of characters. Classify all those that could potentially be characters of a quantum field theory, which means that their expansion in this Q parameter has positive integral coefficients, which we could hope to interpret as degeneracies of states in the CFT of these descendants. And then once you've done that, then look for all CFTs that could be associated to such characters. So this is a slightly different and more bottom-up approach, where you start classifying vector-valued modular functions, and then you put restrictions on them so that they look like characters of a CFT, and then you ask whether those characters really do describe a CFT. So I'll follow the latter approach, and it's the advantage is that it organizes rational CFT by their simplicity. So the number of primary fields will be a basic quantity. That's not the case in these, and in fact, as everyone knows, BPZ's unitary minimal series starts with the Ising model, then the tricritical. By that time, you have respectively 3 and 6 primaries. Then the next is probably POTS with 10. And after that, it's sort of, nobody actually is personally familiar with any CFT after that. We just know there's a series. But if you ask, what's the 15th element of BPZ series, it's something with some calculable central charge and a couple of 100 primaries. And it's, while in this approach, we get all the theories with small numbers of primaries together, and that's somehow a nice way to understand them, because it unifies. So it unifies across this classification, but also gives us new insights into theories which don't fall in this classification for reasons that will become clear as I go along. Okay. Now, yes. Oops. Yeah, you want to have a coffee break? Sure. Yeah, absolutely. Oh, okay. I think it's only 2 more lines and then I'm probably done with the introduction. I'll use the term admissible when the general structure of a VVMF is this above, that each chi I has a fractional power of Q and then all integer powers, positive powers, and the coefficients are AI. So for the ith character, AI0, AI1, AI2 are the coefficients of corresponding powers of Q. And if all these A's are non-negative integers, then we'll call this thing admissible. And I'll show that there are cases where this is not so. Okay, so in this approach, there's one more slide before the introduction ends. The classification of RCFT involves 2 steps, which is 1, classify admissible characters, and then 2, within this set, search for actual CFT. Now, there's some kind of folklore, and it's based on a small number of examples, and we are also, I think, somewhat guilty of it, because in the early examples, it seemed like that if you've done 1, you've also done 2. That is, the moment you get admissible characters, they're probably a CFT. But turns out that too, probably a unique CFT. But this is wrong in both ways. As we'll see to some extent in this talk, and I can discuss it later, most admissible characters literally don't describe any CFT. And also some admissible characters describe many CFTs which have the same partition function. So they are isospectral. They have different chiral algebras, different OPE coefficients, but their partition function is the same. Okay, and in what follows, one result that I'll use somewhere towards the end is that vector-valued modular forms which are admissible and have 2 characters are completely classified. So there's a mathematical work by Banté and Gannon in 2005 which does this implicitly, but more explicitly we worked out. So Banté and Gannon actually is not even for 2 characters, it's more general than that. But we worked this out for 2 characters from a different mathematical starting point in 2018. And this is the one that will be more useful for us for reasons I'll explain. And so this is what I'll present in this talk, the complete classification of unitary CFTs having C strictly less than 25 and 2 primaries, the identity, and 1 more, which is necessarily real. If it was complex, there would have been 3 primaries. And in mathematics language, this is the classification of strongly regular vertex operator algebras with C less than 25 and 2 simple modules. And this is what I'm going to talk about. And the result will be a set of 123 theories, out of which approximately 98, I think 98 are new, or maybe 100 are new in this paper. Yes. So, sorry? 1 less. C is, C is greater than or equal to 1. Yeah. Turns out there are no unitary CFTs with exactly 2 primaries in the BPZ classification. Yeah. So maybe this is the right place to break for. Yeah. No, 2 primaries. It will be precisely 2 primaries, and so it's more special than 2 characters. It won't be counted in our list. And I'll explain why. So since you asked, I'll just say there are certain types of calculations, such as the ones we did in the 80s, where the number of characters is more natural. But there are other things, namely the input from modular tensor categories, where the number of primaries is more natural. And so somehow in writing this paper, we had to balance these 2 inputs, and so we could be sure about our results for 2 primaries. But even if you want to extend them to 3 you could extend them to 3 primaries, which would include those with 2 characters and those with 3 characters. But that would be a separate sort of activity. Yeah. Sorry? Absolutely. Yeah, that's always true. Yeah. Yeah. Admissible is when, so the general structure of a vector valued modular form is this series up here. But in fact, this series and then these chi-i's when Q goes to Q gamma should transform into themselves. But it's possible to find such things where these A's, these numbers, coefficients of each power are not integer, not even rational, not positive. They don't have to have any good property. And so if they are actually non-negative integers, then we'll call it admissible. Yeah, so actually there's one more criterion for admissible, which is that if I is 0, that's the identity character, then A 0, 0 should be exactly 1 and not some other integer, because the vacuum is assumed to be non-degenerate. So there are some more general types of things you encounter which don't satisfy that, but we'll call it a CFT. We'll call it admissible only if that number is 1. Actually should have been written on this slide. Yeah. Sorry, say again. Higher spin CFTs with 1 higher spin current. So the purpose, this method does not specify anything about the number of currents. That's the key point. If you want to classify higher spin CFTs with 1 higher spin current, that's a different kind of activity. Then you would look for representations of the algebra of that current. Okay. Here the whole point of this classification procedure is that we want to classify all theories with a given number of primaries, regardless of which currents and how many currents they have, and what the spins. Yeah. Some if there are any with exactly 1 primary, they'll automatically turn up. You don't have to do anything extra; they'll just show up. Yeah. So AI1 will tell you the number of Kac-Moody currents. Only Kac-Moody currents. Yeah, so you'll look at AI comma S, but then you have to disentangle the contribution to that from all the other lower spin. So yeah, you could imagine a theory which has no Kac-Moody algebra, then it starts becoming interesting. Then you have Virasoro. Then let's say at the Sth level in this, you would have Virasoro descendants, And in addition to them, if you have one more state, then you have got one higher spin current. So yeah, you can actually ask such questions, but yeah, once you have the classification, it's not maybe that interesting anymore. Then you know the theories. So yeah, in any case, we don't find any such. In fact, all the theories we'll find have Kac-Moody algebras. Yeah. No, it's the full set of characters of all of the primaries. So the VVMF is the vector chi I as I ranges from 0 to p minus 1. Yeah, it does. It's plus dot dot dot. No, I is the label of the primary. The Q expansion is, so that's n, ai comma n, or m, whatever you call it. Those of course go on. The powers of Q go on forever. But I just labels which component of the vector is the component of a finite dimensional vector. But each component is an infinite Q series. Yeah. You want to go for coffee now? I guess we just go out and come back in. The Zoom people.
Yeah, for
Sorry.
the Zoom audience, we're going to have a short coffee break for 5 minutes and we'll return.
We are back. Good. Okay, Zoom audience, sorry for that gap. Good. Yes. Question. Yeah. No, even that's not the case. No, yeah, even that's not the case. Yeah, but that one is relatively easy to the point is that once you determine, so I think it is the case that if all these AINs are integer, then I think H and C have to be rational. But let's talk about
How will you get the morphic? Ratios are determined by alpha.
Yes, exactly. The ratios of these A's with each other, like AI1 over AI0 and so on, are determined by the exponents alpha I. So if those aren't rational, and they're determined in a fairly simple way. So if those aren't rational, these aren't going to be integer. Yeah, anyway, I'll show some examples. Okay, I think I went through this. Whoops. Yeah, I was here. Yeah, please. That will come later. That's a technical restriction that we couldn't go above in our paper, but one can try, but I'll explain what that technical restriction is. I mean, the methods up until some point don't really depend on that, but then we'll see that there's a stumbling block at that for reasons which I'll explain. No, it's not actually. No, it's not. It sounds like, but it's not related to that. It's actually related to something about 32-dimensional meromorphic CFT and the fact that we don't know how to classify them. I'll come to it. Okay, so let me introduce some notation and then go on. So X subscript R comma K will be the Kac-Moody algebra based on the simple Lie algebra X of rank R and level K. So here's a summary of the key result in this work. Every CFT with two primaries, and now there's no restriction on central charge, is either the Wess-Zumino-Witten model with one of these four chiral algebras, namely the Kac-Moody algebras A1 at level 1, G2 at level 1, F4 at level 1, or E7 at level 1, which I'll call the MMS set, which I'll explain in a minute. It's either one of these four, or it's a coset of a meromorphic CFT by one of these four. This is the main theorem. And in order to explain what it means, I need to discuss meromorphic CFT, which is what I'll turn to next. But is the statement, I mean, I can't ask you if the statement is clear since I haven't explained coset or meromorphic theory, but yes. Yes, exactly. rank is of the simple D algebra. So here A1 is literally is SU2 at level 1 and G2F for E7 are well known exceptional algebras. Okay, so let's turn to a discussion of meromorphic CFT. So meromorphic CFT or one primary CFT are those which have only one primary, and that has to be the identity. So it means that everything in every state in that theory is a descendant. Oops, what happened? We're back. Okay. Every state in the theory is a descendant under the chiral algebra, and it's a theorem that they exist only for central charges that are a multiple of 8. I'll give you a few scattered results that we'll need, but I can't go into the full detail. Obviously, if there's only one primary, then there's only one character, and the partition function is the mod squared of that character. And this character needs to be modular invariant up to a phase, so that Z is modular invariant. So it's a one-dimensional VVMF, but it's still allowed to pick up a phase under modular transformations. Now, from this, one can prove that chi is a function, suitable function. Suitable means to be in order to be admissible of the Klein J invariant, which is this very famous function of Q, starting at Q inverse and then with these positive integral coefficients. This J is completely modular invariant. So it's weight 0, it doesn't pick up any factor or any phase, and it's just invariant under all of SL2Z, and it's the unique function. So it's called the Haupt module because from it you can generate all modular invariants of SL2Z. Okay, so some examples, yes. Yeah, so the word yeah, exactly. So well, I'm not sure what the reason is, but one reason is that, yes, this has a first order pole as Q goes to 0. So that's, while for other CFTs, this is a fraction. So it's more like a branch cut at infinity. This is an actual pole. So that gives it the name meromorphic. Turns out mathematicians call these holomorphic vertex operator algebras. So they don't seem to, I mean, in that terminology, you just maybe ignore the pole. But there's another thing, which is that correlation functions have singularities which are also meromorphic in nature because all conformal dimensions are integral. Because everything is a descendant, descendants have integral dimensions, so every field has integral dimension, and so every 2 or 3 or 4 point function, its short distance singularities are of the form 1 over Z1 minus Z2 to some integral power. So it's meromorphic also in that sense. Yeah, exactly. So exactly this. So if you take J to the 1/3, that's not modular invariant up to a phase. Sorry, that's modular invariant only up to a phase. J is modular invariant, but its 1/3 power is invariant only up to a phase. And yeah, there is. There is. So J actually, in some sense, I mean, if you perform a modular transformation and do it, appropriately, then J picks up e to the 2 pi I, which is 1, but then J2 fractional powers pick up phases, 1/3 or 2/3, e to the 2 pi I times 1/3 or 2/3. Those are the only ones allowed. If you try to take any other power of J, what you end up finding is that it's no longer admissible. It's already not obvious, right, from this. If I take the 1/3 power of this, you'll get some new set of coefficients, but how do you know they'll all be positive and integral? Turns out with the 1/3 power they are, with any other power they are not. That mathematicians have proved. We don't have to. I mean, you can try it, but it's just something known. No, there's a deeper theory which comes from the fact that J vanishes at a cusp of moduli space, which is this corner, the corner of moduli space. So these points, and these points are points of order 3. So and it vanishes there. So if I take a 1/3 power, nothing goes wrong there, and somehow that's the underlying reason. Okay. Yeah. Yes. Yes, you can do that, of course, correct. So j to the 1/3 is known to be the character of E8 at level 1. I should have written E8, 1. All these things here should have had level 1 on them. So at c equals 8, there's a unique meromorphic theory which has character j to the 1/3. At c equals 16, there are two isospectral theories. So they both have the character j to the 2/3, but their Kac-Moody algebra is either E8-1 cross E8-1, or the thing which in physics we call SO32 or spin 32 by Z2, but is more properly called D16 plus. So D16 is SO32. The plus means that it's some extension of it which has only one character. So naively, if you look at D16 plus, it has a bunch of representations, but there's I'll explain extension in a minute. There's an extension of it which is meromorphic, and that's the one which appears here. And as people probably know, this fact that these are the unique meromorphic CFTs at c equals 16 gave the basis for the heterotic string, which required you to match a 26-dimensional sector and a 10-dimensional sector. The deficit is 16. The only way to achieve, at least in the beginning, the only way to achieve modular invariance seemed to be to have a meromorphic CFT for that 16-dimensional space. And yeah, in fact, then one in that system, one only takes chi and not chi bar. So you actually have the phase. There is a phase here, but then you have to combine it with the superstring in a way that the phase cancels and you get modular invariance. So that all can be done, has been done. Now things become interesting at c equals 24. Because now the character, the simplest thing you could do is just consider j, and it's the CFT E8 cubed, E8 level 1 cubed, but you can add any integer to it, and it's still admissible. Any positive integer, or in fact, even any negative integer greater than minus 744, because any integer you add will contribute to this term. And obviously, a constant is modular invariant. So everything is, all these j plus n's are all admissible, but in fact, a few of them for specific values of n come from lattices in 24 dimensions called Niemeyer lattices. And as I'll explain in a minute, most values of n don't correspond to any CFT. So this is the first place you see this fact that an admissible character is not a CFT, not necessarily a CFT. At c equals 32, you have to take the 4/3 power of j, but you can also have a subleading term. So you still have this free parameter n. And examples of these are provided by even unimodular 32D lattices, many of which are known, but they're not completely classified. So, yes. The n's which are, yes, they will. And the reason is that for any theory in 24, you can multiply it by E8 and get a new CFT. Yes, there are many. Yes. So that's probably my next line. So let me just say all these examples correspond to C free bosons compactified on a torus RC mod gamma, where R to the C mod gamma, where gamma is an even unimodular lattice, and we'll call them lattice theories because they are just free boson theories where the bosons are put on a torus defined through a lattice. No, you can't have any of those. No, not possible. You just don't, n has to be 0. Exactly. That's the point. Yeah. So the reason why is that is this reason, this picture I drew. So if you add n, the 0 moves from there to somewhere else. And now if you take the 1/3 power, you'll start getting singular behavior. Yeah. Okay. But there are more general examples starting at c equals 24, which are not lattice theories, which means it's a meromorphic CFT, but it's not associated to any free boson system on a lattice. It's just a meromorphic CFT which exists for reasons which remained obscure for many years until mathematicians eventually showed that these non-lattice possibilities are all orbifolds of the lattice possibilities in the case c equals 24 only. So, but the orbifolds are quite generalized orbifolds. They're not completely geometric. So it's quite a complicated subject, which I'm a little bit struggling to learn right now. But for now, just take it that there are some lattice and some non-lattice theories. The lattice ones are easier to construct, the non-lattice ones are harder to construct, and that's why the complete classification at C equals 24, which I'll come to now, was a big achievement. Yeah.
Also have this form.
Yes, the form is, so these are actually, so I should have said, these are actually the admissible characters. So anything that you can have at C equals 24, if it's a CFT, will be of the form J plus N. There's nothing you can have not of this form. But in looking for which N and the definition of the theory and what is its chiral algebra, which varies a lot, you need to fix both the allowed N's and then also within that find out how many theories there are. And within those, there are lattice and non-lattice possibilities.
All these examples are the right hand.
Sorry, right hand side, this? Yeah. So here I've only given lattice examples. It's just, they are just examples. Yeah, actually that's right. So that may be the misleading point. Yes. Left side includes these are the most general admissible characters in their dimension. These are examples of lattice theories which realize these. And then there are examples of non-lattice theories, but they don't appear in the first two rows. They appear in the third row, and from fourth row onwards, they should appear also. And I'll come to that now. So now comes the first, I would say, interesting, very non-trivial result in this thing, which is Schelekin's classic work of 1992, where he showed that among admissible characters of this sort, there are precisely 71 meromorphic CFTs. And actually, he didn't show it. He argued it, and it's one of the features of his argument is still slightly conjectural. So let's come to it. So out of these 71, 24 are lattice theories. These are the Niemeyer lattices. So it's a weird coincidence that in 24 dimensions, there are 24 even self-dual lattices. Just a fact. Then there's a finite number of generalizations involving orbifolding. And I think these two examples will a little bit help you get a feel for it. Here's a lattice theory. Its Kac-Moody algebra is this: A11 at level 1, D7 at level 1, E6 at level 1. It's the direct product of all these. Or as a finite Lie algebra, it's the direct sum of these. Now, it's well known that for lattice theories, the only algebras, Kac-Moody algebras that arise when you compactify bosons on a lattice are of ADE type, and they are at level 1. So when you see ADE at level 1, all of these, then you know it's a lattice theory right away. Not only that, 11 plus 7 plus 6 is 24. So the sum of the total rank of the Kac-Moody algebra is the dimension, is the central charge of the theory. And so there's one of the Niemeyer lattices. And this Kac-Moody algebra is actually the algebra of the root system of the lattice. So the lattice has a set of points relative to some origin of length squared 2, and then you have some some way of finding Lie algebra products or commutators between them, and from that you can deduce that this is the full Lie algebra of the root system of that lattice. Okay. The second example is a non-lattice theory. You see that it's non-lattice from the fact that this D7 arises at level 3, so it can't come from a lattice, and also that G2 shows up, which also can't come from a lattice. So it's a non-lattice theory. You also see that 3 plus 7 plus 2 is not 24, misses by quite a lot. So the rank of this algebra is not equal to the dimension or to the central charge of the CFT. Okay, so it's just there. Now, how did Schelekin find it? He found it by basically scanning all Kac-Moody algebras, first proving some basic theorems and then scanning all Kac-Moody algebras for those which could contribute the right central charge and the right dimension to be a meromorphic theory, and which for which you could find one modular invariant character by combining the characters. So the second one is a generalized orbifold of one of the first of the lattice theories, and there's a certain sense in which all the lattice theories are also orbifolds of each other. It's actually a very beautiful system that's emerged from this study, which is that the Niemeyer lattices are themselves orbifolds of a particular one called the Leech lattice, And then the non-lattice theories are generalized orbifolds of the lattice theories. The lattice theories are ordinary orbifolds in the sense some geometric involution, twisted sector, and you get the new lattice. But I think for these, it's more complicated because the involution might not be just a purely geometrical action. So the one lesson you learn, yeah.
71 CFTs.
Yeah.
What was the starting point? I mean, you have to assume some chiral algebra.
Yeah. So actually, what he did was to argue that okay, first of all, there's one character, J minus 744, which has no Kac-Moody algebra. Okay. If you look at this, expansion, if you take n to be minus 744, that's gone, and that's the dimension of the Kac-Moody algebra at the end. 744 plus this integer, because it's the first level descendants. So he argued that there should be one theory like that, which was already known before he wrote his paper. That's the so-called monster CFT, and it can be constructed by taking the Leech lattice, which has actually a Kac-Moody algebra of dimension 24, which is U1 to the 24, and orbifolding in a way that projects out all 24 U1s, leaving nothing. You have to orbifold cleverly so that the twisted sector doesn't bring back some Kac-Moody algebra. So there's the monster, then he puts it aside. And what's not proved, I think, till today is that that character, J minus 744, uniquely describes the monster. I mean, we know that the monster is described by it. We don't know whether there's another CFT that it describes. After that, he could argue that the remaining cases are one case with U1 to the 24, where n is minus 720, which is the Leech lattice. And then all the remaining cases must necessarily be direct sums or direct products of non-abelian Kac-Moody algebras. Once you get that fact, then you can enumerate those. It's very tedious, I must say. And so this comes out of that enumeration. Again, the first set he didn't have to enumerate because Niemeyer had solved that problem. But the second set is largely due to him, but some of them came from earlier studies also by him and others in the heterotic string vacuum. So the history is quite fascinating. Yeah.
Turning the Kac-Moody algebra from n and n, so then all the add expansions are just part of the Kac-Moody.
That's right. Something, yeah. So I think you only need to go to some orders. In spirit, it's very similar to the way we were thinking about things, and it was few years later. But I don't think he knew much about our work, and at that time somehow there was not much connection. One of the main points today is that what we did in the 80s is closely related to this, which we didn't know and we couldn't have known since this was 4 years in the future. One lesson to take away from this is, supposing I actually take Vesumino-Witten models for A11, D7 and E6 at level 1 and I multiply them out, I'll get a couple of 100 characters, right? Because A11 has already a dozen or so characters, and this will have some number, and some number I'll get something of order 200. And the statement is that there's one linear combination of all these roughly 200 characters, which is modular invariant on its own. It's some kind of modular miracle. And that's the underlying mechanism by which you find a meromorphic theory out of this kind of thing. And what's important is that unless you add or multiply the right Kac-Moody algebras, you won't find the meromorphic extension. I mean, in general, A11 one may not have or does not have a meromorphic extension, nor does D7 one, nor does E6 one, but the product of all of them does. And the meromorphic extension will consist of looking at all primaries of this product system and finding the ones with integer dimensions, then adding them all up with some coefficients and showing that the result is j plus n. And again, you only have to check a few terms because after that it's sort of guaranteed if you can show that that's modular invariant. Okay, so I hope this gives some insight into how meromorphic theories arise. Yeah. No, because the Vesumino-Witten theory is modular invariant, but it has a number of characters. And what you have to do here is to extend the chiral algebra. So what happens when I take linear combinations of characters of such a system, there'll be spin 2, spin 3, spin 5, various random spins coming out by multiplying, say, I have a character of A11 and a character of D7 that may add up to have a dimension, say, 3. But now if I add that character to the identity character, I'm introducing a new chiral generator of spin 3. Okay, so that's the extension of the theory, which is meromorphic. I don't think so, because actually if there were, then the problem for central charge 32 would be doable, and it's not doable. So as far as we know, so I don't think so. Yeah, Subrat. Okay, so 70 of the 71 Shelikin's theories are of this form. They are meromorphic extensions of non-simple Kac-Moody algebras obtained by taking multiple different algebras and then finding the extension. The 71st is the one with no Kac-Moody algebra, and it's associated to the monster group, and it's known as the monster module, because the degeneracies of states at every level are exactly the dimensions of irreducible representations of this largest sporadic discrete group, the monster group. Now coming to C equals 32, at 24, there were 24 even self-dual lattices. But at C equals 32, there are at least 10 to the 9 even unimodular lattices, billion. And then there should be a corresponding number of non-lattice theories. I mean, that also is, at a minimum, there should be that many. And nobody has tried to classify them. Something is known about the ones, about these. For example, among them, only 132 have complete root systems, which means that they are pure Sugawara CFTs, and those are called curvaire lattices. But there are other lattices where the Kac-Moody algebra doesn't take care of the whole central charge, if you like, for the free boson theory. And so those are harder to deal with. So complete classification at C equals 32 is pretty much impossible, or that's what's considered to be the case today. Okay. Any more questions? Then I'll move on to the to some history, and then I'll come to the complete classification. So as far as history goes, this is where it started for us. So Samir and Ashok and I in 1988 proposed a scheme to classify admissible characters for initially 2-character RCFT. I'll summarize the scheme in a few minutes. And then after finding admissible characters, we used various techniques to try and understand what CFT they describe, if any. And it turned out that in some sense, they all described CFT. So at that time, it certainly looked like once you have found admissible characters, you have found CFT. And I'll be able to explain now why it seemed like that at that time and why it doesn't seem like that now. And it has something to do with the existence of free parameters in the admissible characters. So I just showed you in the case of meromorphic theories that at C equals 24, you get a free parameter. So J can be generalized to J plus N. An analogous phenomenon happens for any rational CFT. And it's there that the admissible characters now no longer correspond to CFTs in general, and you have to look for the CFTs. Yeah, so there were some mysterious ones, and sometimes I like to talk about them, but today in the interest of time, it's now called an intermediate vertex operator algebra, which is remarkably, it's a small field of maths that we started inadvertently. No, it won't be, for the reason that, it's not, so we won't count things of that type at all. That's right. Okay, so the classification is by 2 integers, n, which is the order of the differential equation, which will determine the number of independent characters. And we'll be careful in a moment that n in general is greater than the number of primaries. So I'm going to pick out from this work the theories which have only 2 primaries, because those are the only ones I'm interested in today. So the case of interest for today is n equals 2, but more specifically also p equals 2. The second integer in this classification is the Wronskian index of a differential equation, and this I need to explain. And this comes from the fact that any vector valued modular form can be thought of as the n independent solutions of a linear differential equation in tau, which is modular invariant. And it's a part of a more general rule, which is that if I have a bunch of functions that rotate into each other under some symmetry, then I can find a differential equation for which is invariant under that symmetry, but the solutions don't remain invariant under the symmetry, rather they mix. And differential equations of this type are called Fuchsian. They have some regular singular points, and that's the reason why this phenomenon happens. And I'll show you actually in the simplest case, I'll derive this statement, the first line, that you can find a differential equation given the solutions. So what we did was to write the most general such differential equation and examine its solutions, sort of scan them for admissibility. Now, the most general second order modular invariant differential equation in tau is d tau squared plus a function times d tau plus another function on chi equals 0, where d is a covariant derivative which has this connection like term in it proportional to E2. It's called the Ramanujan-Serre derivative. So it's a covariant derivative mapping modular forms to modular forms. If you use that in the equation, and also if phi 2 and phi 4 are modular of weight 2 and 4, then this whole equation will get a factor in front, which is common. And so the equation, if it was 0 before, it will be 0 after, and therefore the equation is modular invariant. So phi 2 and phi 4 are modular of weight 2 and 4, but in general, they are not holomorphic, they are meromorphic. But the solutions chi will be holomorphic. So let's explain that. Here's a very simple explanation. Supposing we know a pair chi0, and I'm just doing it for 2 dimensions. We know a pair chi0 and chi1 which form a vector valued modular form. And I want to write the condition that a general function chi is a linear combination of these two, chi0 and chi1. Well, obviously, if chi is a linear combination of chi0 and chi1, then this 3 by 3 determinant is 0, because the last column is proportional to the sum of the first 2 columns. If we expand this by the last column, we get a differential equation for an unknown chi with fixed coefficients. Okay. And now if we divide by the determinant up here, then we find that we have our MLDE. So this is the proof that given a VVMF, you can get an MLDE, of which the VVMF are its solutions. And you also see that phi 2 and phi 4 are derivable if you know the solutions. And of course, the solutions are derivable if you know phi 2 and phi 4. So it's both ways. And you also can see from this why phi 2 and phi 4 could have poles. It's because of these denominators. So the chi's are perfectly holomorphic, but you're dividing by something. And oops, I did something terrible. Yeah, you're dividing by something, namely this, which is called the Wronskian determinant. And if it has zeros, and if they're not cancelled by zeros in the numerator, then these will have poles. Okay, how many poles can we have? Well, the number of such poles in the interior of moduli space is parameterized as L by 6, where L is a non-negative, I don't know why I wrote it this way, L is just 0, 1, 2, 3, etc., except 1. Okay, and the reason is L equals 0 simply means it's pole free. L equals 1, okay, L equals 6 means that there's a single real actual pole, and that means in terms of this drawing of moduli space that the pole is somewhere in a generic place in the moduli space. It's an entire pole. But because of these cusps at the corner of moduli space and also at this point tau equals I, you can have a half order pole here and a 1/3 order pole here. And that's why L can be 2 and 3. But once it can be 2 and 3, it can also be 4 and 5. Because twice of 2 gives you 4, combination of 2 and 3 gives you 5. So if there's a pole here and here, you get 5. If it's only here, you get L equals 2. Here, L is 3. If there are 2 poles here, it's L equals 4. And once it becomes 6, then the pole sits inside the moduli space, and then it's actually an integer. So the number of poles is fractional because the moduli space has cusps. So that's why we parameterize it with this number L, which is not actually the number of poles, but 6 times that. So this is explained here. And for a long time, L didn't have a name, but at some point I thought, let's call it the Wronskian index. That seems to work because it comes from the Wronskian. Now, actually, Nesulich proved a very nice thing in 1989 that when you have 2 characters, then L actually is restricted to be strictly even. So 0, 2, 4, etc. For any given L, there's a finite basis of functions of these 2 Eisenstein series E4 and E6 which are a basis of modular forms, which can be used to give these coefficients phi 2 and phi 4 in the differential equation. And for this reason, if I restrict L to be some small value, then the modular differential equation will have very few parameters. And that was very crucial. That's why we needed to restrict L at all. If you don't restrict L, then even for 2 characters, the modular differential equation can have an arbitrarily large number of parameters, and there's not much you can do with it. Okay, is this point clear? If there are any questions? Okay. For future reference, there's a nice relation between the Wronskian index, the central charge, and the conformal dimension in this 2-character case, which actually is an example of a more general relation which holds with any number of characters. And basically what it's doing is telling you the sum of poles and zeros in a certain way. And so L is actually C by 2 minus 6H plus 1. And I'll come back to that in, I'll need that later in the talk. Okay. Now H is the single conformal dimension of the single non-trivial primary. That's there by assumption. But in general, you get a sum over minus C by 24 plus HI, and with some factors in front. So the analogous formula holds. I've just kept the formula simple for 2 characters. Okay. Now we fix L to be various small values and try to scan the parameter space of the differential equation to look for admissible solutions. And in order of simplicity, we start with L equals 0. Then there's no weight 2 modular form which is completely holomorphic. So phi 2 must be 0 and phi 4 must be mu times E4. And so this is the MLDE. D tau squared plus mu E4 of tau on chi is 0. And here you can see that by specifying that there are 2 characters, so second order, and that L is 0, I've got a differential equation which has only 1 free parameter. And for every value of this free parameter, the 2 independent solutions will be a VVMF. That's by construction. So the only thing you have to worry about is if that VVMF is admissible or not. And is the only, I mean, mu determines everything. It will determine the central charge, it will determine the conformal dimension, which are not independent inputs because of that Riemann-Roch theorem, and it will determine all the coefficients A, I, N in the expansion of the characters when you solve this equation. And this equation now has been named after us by mathematicians, which feels nice. So yeah, I said this already, the parameter mu completely determines the solutions, except for overall normalizations, which actually is important. Okay. Now it's good to parameterize the leading terms of the solutions as q to the alpha 0 and q to the alpha 1, where alpha 0 is used to define a number c by saying alpha 0 is minus c by 24, and alpha 1 is then used to define a number h. Okay. The idea is that if these solutions correspond to a CFT, then that CFT will have central charge C and the primary will have dimension H. If they don't correspond to a CFT, it's just some parameterization which has no meaning. But it's useful to think of it this way. Next, we solve the MLDE recursively by the Frobenius method, which is to just insert a leading solution q to the alpha, try to fix the coefficient, the exponents alpha in terms of that mu, and then look for the next order correction and then plug it back into the equation and determine these expansion coefficients. Now, the best way to understand how this works is to see 2 examples. If you choose, and it's not difficult to find, if you choose the value mu in that equation I wrote to be minus 119 by 3600, you'll find that chi 0 and chi 1 come out like this. And you see that chi 0 is beautifully admissible. It starts with 1 and all these coefficients are integral and you can compute to any order you like and they keep being positive integral. Chi 1 is like that except for a 7 in the denominator of this term, 34 by 7. So if you normalize this by multiplying overall by 7, which are always allowed, the differential equation doesn't tell you that, then this will start with 7 and then it turns out everything else is integral. Okay. So, yeah. Yeah, exactly. So I multiply the whole thing by 7. I get rid of that 7. If I normalize this by multiplying by 7, then the first term becomes 7, the next term becomes 34, and all other terms are already integer, and they might be terms here which are not integer, but they are no worse than 1/7 fractions. So they'll all become integer if you multiply by 7. Yeah. Yeah. Ashok reminded me to say that. I had forgotten to say it, but I did say it eventually, that the first term is 1 is part of admissibility. Yes. For the first character, the identity character, it should always be 1. Okay. Now, once you do this, you can read off a lot of things. First of all, from this exponent, the central charge is 14/5. From this exponent, the conformal dimension is 2/5. From this number 14, the dimension of the Kac-Moody algebra is 14. And from this 7, the degeneracy of the primary is 7. So you need to look for a you need to look for a Lie algebra of dimension 14 with a 7-dimensional representation. And then, of course, these central charges. And it's very easy to see that you land on G2 at level 1. G2 has dimension 14. Its fundamental is 7-dimensional. And this is its central charge and conformal dimension. Now, supposing I chose a neighboring value, very close value to this one, -143/4800 for mu in the differential equation, then this is what the solutions would look like. And what you can see is that these solutions have no hope of ever being admissible, because as you go down the series, the denominators grow without limit. Okay, so there's no integer that you can multiply it with throughout, which makes it integral. Okay, so this is a classic example of an inadmissible character, and this shows you that there cannot be a 2-character CFT at central charge 13/5 with Wronskian index 0. Because if there's no admissible character, then there's definitely no CFT. Okay, so I hope this point is clear. This is what I mean by scanning. So we vary mu. Whenever it hits a value where everything looks very good, then we say this is admissible. And most of the time, it doesn't hit any nice value. And it could be irrational or rational, but when it's rational, if things start to look like this, then it's equally bad. It's just not admissible. And it's not that we pull these values out of a hat. We first start with the first coefficient, the coefficients of Q, and we start to see how they're looking. Then we look at Q squared, and you keep getting constraints on mu until you find a finite set, which gives admissible characters. And this is the finite set. This is a screenshot from our 1988 paper. So I'm not going to go into the details of this question mark theory. This is what Ashok was saying. It has to do with E7.5. But as you can see, the rest of them are all nice unitary Kac-Moody algebra. So Wess-Zumino-Witten models at level 1. And they come together in a very nice way. Many years later, Deligne found some numerology of Lie algebras which precisely combines these same set of algebras. But I don't know why, and I still don't know why that should be related to this, because this is about Kac-Moody algebras and that's just about Lie algebras. But it's an interesting fact. Okay, so I'm going to, yeah. So now, this is good, but many of these have actually more than 2 primaries. For example, SU3 has 3 primaries, the 1, the 3, and the 3 bar. So we have to get rid of those for today's talk. After we get rid of, okay, and E81 has only 1 primary. So we get rid of that. We want exactly 2 primaries. And A21, D41, and E61 have 3 primaries. So we get rid of those. Actually, D4 has 4 primaries, of which 3 have the same character by triality. Once you get rid of that, you land on what I call the MMS set, which is only these 4 theories. And these are their central charges. They happen to lie between 0 and 8. But please note, we didn't restrict the central charges at all. Just they happen to lie in this range. We did restrict the number of primaries and the Wronskian index. Okay. Now, as a technical point, we did not show in 1988 that these are the unique CFTs which describe our 4 admissible characters. We only showed that there is a CFT for each of them, and it's a simple one. In 2018, these mathematicians actually proved that this identification is unique. Okay, so now actually, yeah.
Primary theories are also for all 2 characters.
All 2 character theories, actually. Yeah, the MMS, the full MMS. So actually, it's only in this paper of mine that we restricted to 2 primaries. And I'm not completely sure that we couldn't have done the remaining cases, but anyway, this came out well. So, and somehow for mathematicians, somehow this is more natural for the vertex operator type of people. Okay, now obviously I can't tell you, it's going quite slow. How much time more should I take? Yeah, it will be done in 20 minutes because all the groundwork is laid and now I can take you through results. I don't have to derive anything. So the L equals 2 equation. So remember the Wronskian index is 0, 2, 4, 6 and so on. And the 0 case was done by us in 88. Now Nesulich in 1989 actually tried to generalize it to L equals 2 and he found some provisional solutions, but he didn't manage to identify them with CFTs. And in 2015, I revisited this problem with my master's student and confirmed his discovery of solutions to the MLDE. This is a new coefficient in the MLDE now. And among those solutions, which are about 9, 4 of them are the ones which have 2 primaries. Again, the others have more than 2 primaries, so I'm not showing them to you here. And these are the values of the central charges. Now, in case you memorize the central charges on the previous slide, you would notice that these numbers are 24 minus those numbers. So there we had 1, 14 by 5, 26 by 5, and 7. And if you subtract those from 24, you get these numbers, which is very suggestive. Moreover, we know the conformal dimensions for these, and they are also 2 minus the conformal dimensions on the previous page. So that's very suggestive, but that's where it stayed for a while. Until I actually visited ETH and talked to Matthias Gabberdiel about this, and we figured out what was actually going on and what these theories are. Yeah. There are all the cases of 24 minus C relative to the previous slide are there. They have higher numbers of primaries. The number of primaries always matches exactly. So the way we understood this fact was by using a variant of the coset construction of rational CFTs. And it's a funny thing that the coset construction as popularized in the physics literature and embodied in the yellow book on CFT is a more complicated one because the simpler one had never been explored in any detail and definitely not in the physics literature. In the maths literature, it was sort of alluded to a little bit. So I'll explain the difference. In the physics literature, the coset was generally written as V1 over V2. These are actually calligraphic V's in the mathematics notation. V1 over V2, where V1 and V2 are both Wess-Zumino-Witten models. You basically divide one by the other. And you can do this if the Kac-Moody algebra of the denominator theory is a proper subalgebra of the numerator theory. And a famous example was that if I take A1 level K cross A1 level 1 over A1 at level K plus 1, I reproduce the unitary minimal models. Okay, so this is a kind of coset that was popularized and in the 80s. And so they're defined by this embedding. There are certain conditions, so you can't just embed anything in anything. Levels also are important to determine what you can embed in what. Now, one obvious consequence is that the central charge of a coset is the central charge of the numerator minus the central charge of the denominator. So that's just a fact. Okay, but the cosets we need are simpler. In our coset, the numerator is not a Wess-Zumino-Witten model with many characters and many primaries. It's a meromorphic theory with just one primary. And we divide it by anything that can embed in it, and we get a coset pair. And what I'm going to argue is that the L equals 2 theories are the V primes obtained by dividing Schelekin's list of 71 theories by V's, where V's are the MMS set with L equals 0. Now, such cosets had been sort of alluded to. I would say that in these papers you find a passing reference. This axiomatized the coset construction in the maths literature and quite clearly included such examples, and they keep coming up in the maths literature, but until our paper with Gabberdiel, it had never been really explored in any concrete examples. So these cosets are also defined by embedding the Kac-Moody algebra of the denominator and the numerator, but they also exist more generally. For example, even if A and V don't have a Kac-Moody algebra, the precise statement due to Frenkel and Zhu is that you just have to embed the chiral algebra as a subalgebra of the bigger chiral algebra, V in A. As long as you can do that and find its commutant, you've got a coset. Now, since A is meromorphic, the denominator V and the coset V prime are both P-CFTs for the same number of primaries. This was not the case in the Goddard-Kent-Olive cosets. So it's actually simpler because, and in fact, there's one way to see it is that there's a kind of dot product relation between the characters of V and V prime. If I take these and dot them with each other and sum and with some integer coefficients, then you get the character of A, the modular invariant character of A. And this is kind of called the bilinear relation or gluing relation. It looks a little similar to how we made a partition function by gluing chi with chi bar. But here we are gluing chi of one theory with chi of a different theory. So it's completely holomorphic. Both sides depend only on Q. There's no Q bar dependence. Okay. So let's show an example. I already showed you number 34 in Shelikins's list, A31, D73, G21. As an affine theory, this would have about 200 primaries, but there's a one primary extension, which is the Shelikins theory, number 34. And now we can divide this by G21, which is in the MMS set. And the way we divide it is that we just cancel this. So we are left with A31, D73. And now this doesn't have a meromorphic extension, but what it does have is a two-character extension. And that's precisely obtained by this coset. So this coset completely defines it. And the central charge of this is the central charge of the C equals 24 theory minus the central charge denominator theory. That's 106 by 5. And that's exactly one of the four central charges that we were trying to explain in this slide. 106 by 5 is the third entry in this slide. Okay, so here's an example how it works. Yes. Yeah, so good. Thank you. So it's certainly true that you can always take the coset by taking the rules are well defined. That's the short answer. But there are actually two non-trivially different ways of doing it. One, the denominator happens to be a factor sitting in the numerator. So you just delete it and you keep what's left. The other, yeah, but that's easy to do by the bilinear relation because now G21 characters are known. And Shelikin's 34 character is known. So, yeah, because it's embedded by cancelling this. So the numerator is known as a linear combination of characters of all of these. So in particular, you know where the G21 characters are, and you just pull them out, and whatever you get which multiplies them is the coset character. So it's quite easy, actually, very explicit also. And so, but this is a kind of quotient where we just delete a factor, but you could ask, why can't, yeah, coset has, exactly. Not only that, there's a formula which says that such quotients, in the case of two characters and the upstairs theory having central charge 24, the Wronskian index of the quotient will be exactly 2. I keep doing this. So you can work out the formula for the Wronskian index of the coset given the central charge of the numerator and the Wronskian index of the denominator, and it lands on L equals 2. That's what we were trying to explain. So it turns out that there are 13 such CFT in total with these 4 central charges. So some are isospectral and they correspond to these 4 MLDE solutions. So this completely explains the structure of the L equals 2 solutions. Yeah. What I was trying to say is you could also take G21 and try to embed it in A31 or D73. Now in this example, it turns out it doesn't embed. So there are precise rules for embedding. But if it did embed, then you would have a commutant of G21 in A31 and that would survive in the finder. So those are what I call non-trivial embeddings, much harder to do, but they are actually the ones we had to do in the present paper to get all the new theories. The easy ones are the ones where you just look at a the Kac-Moody algebra and delete one factor corresponding to the denominator, then you know everything without learning too much group theory. But to embed the denominator non-trivially in numerator factors, you need to know more group theory. Okay. Now for L equals 4, the MLDE can be again solved, and this time the solutions can be identified with cosets of a C equals 16 meromorphic CFT by the MMS set. It just comes out from the formula. And so you can take E8 cross E8 at level 1 and divide by each of these. Now you have to actually embed each of these denominators into one of the E8 ones. That's the only thing that's allowed. But beautifully, the commutant of A11 in E81 is E71, and conversely of E71 in E81 is A11. And similarly, G2 and F4 are commutant pairs in E81. So the end result has Kac-Moody algebras like this. So you could also have discovered this set by tensoring the E8 character with the original MMS series. And it turns out the E8 character has L equals 2. So if you tensor it like this, you get L equals 4, 2 from each character. So that's a side remark. If that wasn't clear, don't worry. But here we get four theories. Yeah. Yeah.
A11 would be like, not this one. I mean, our silicon string that we discussed.
Yes. Yes.
Here you could have quotiented by A11 also.
Yes, of course. So we have to do all of them. So A11 is an example. Yes.
That's also one of the.
Yeah. So now comes the interesting thing. If I quotient by A11, so A11 is sort of a friendly subalgebra which embeds readily into lots of things. So if I tried to take this divided by A11, I would have to embed A11 in A31. But I can show that that won't give me L equals 2. So if A11 is in the yeah, it will have L equals 8 actually, it turns out. So if I want L equals 2, I have to pick from the Shelikin's theories. And if I want my denominator to be A11, then I have to pick numerators which contain A11. So that it's like that. And he has a, you can always do this. Yeah, then you just delete it. So for each, so you recycle through the 4 MMS theories, A1, G2, F4, and E7. And for each of them, you scan all the Shelikin's theories, and wherever there's a visible factor, you delete it, you get a coset theory, and that's what leads to 13. In this case, it's non-trivial embeddings. Now here's another one. Of course, since E8 cross E8 could be done, you can also do D16. Now it's really interesting, because F4 and E7 cannot be embedded in D16. So there are only A1 and G2 embedding in D16. And if you look at the commutant of A11 in D16-1, the commutant is A11, D14-1. If you look at the commutant of G21 in D16-1, it happens to be B12-1. These are all you look up from various Lie algebra tables. Okay, so now there's a puzzle. In the first case, A11, D14-1 has central charge 15, right? Because because these are simply laced and the total central charge of these is 15, and that's 16 minus 1. So you're good. But in the second case, the central charge of B12-1 is actually 25 by 2. And that's not 16 minus 14 by 5. Okay, so even though the coset has the Lie algebra only B12-1, it's not an extension of B12-1 only. It has some other CFT in it, and that deficit is 7 by 10. Now, because of unitarity, you can tell what that means. It means that there's a tricritical icing module also, and so this coset is not defined by only a Kac-Moody algebra, but by the product of a Kac-Moody algebra and the tricritical icing model, then extended to make a two primary theory. Without this contribution, you couldn't extend B12-1 into a 2 primary theory, and anyway, it would have central charge 25 by 2, so it couldn't be this coset. This is now becomes a generic phenomenon for us, that these minimal models keep appearing in the cosets in many cases. So we learn an important lesson. There are 2 character extensions. Yeah.
It's also well defined at the level of origin.
Yes, because it's basically defined at the level of chiral algebras. These are ultimately they are representations of chiral algebras. And about correlators, I'll tell you later. I have written one paper on correlators of cosets. There's quite a lot that could still be done, but that seemed to work out. Okay, so this is an important lesson. And to summarize, we found 6 two-primary CFT with L equals 4. And now I can finally tell you the theorem and then list the classification. So now it becomes very fast. So we can continue this process. We can keep taking cosets of meromorphic theories and generating many CFTs, and the values of the Wronskian index will keep increasing. But how do we know it's complete? So it turns out for the two-primary case, you can prove it's complete. And therefore, the theorem that every theory with two primaries arises as a coset of a meromorphic theory by the MMS set. This is the theorem. So let me explain why it's true. First of all, I emphasize that it's a non-trivial statement, that there cannot be anything missed if you list all such cosets. And it's easy to prove for exactly two primaries, but it's not yet proven for general numbers of primaries. But it is actually, we conjectured that it's true in general. And mathematicians seem to think it might be, but I think the agreement is that there's no proof right now.
If you relax the constraint that we have two primaries,
yeah,
just take two characters.
Yeah.
Then it is not true that every two character theory
probably it's still true because the two character theories have usually 3 primaries at most. Some have 4. I think for 3, what I'm saying might still be correct. I'm not 100% sure. Yeah.
Below the character, whether what is left also has the same.
Yes, it has the same number of primaries. That I'll actually, yeah. And
those primaries will have the same character after pulling them out,
right?
Then it will become again a reduced number of primaries.
Yes, yes. It will be exactly the same. Namely, if I take a coset of a meromorphic theory by theory with n characters and p primaries, the coset will have n characters and p primaries. Both will be true. N characters that it will have is obvious because of the way the coset works, but p primaries also turns out to be true, and with coincident characters, everything will be the same. Yeah, okay, so let's look at the proof of that statement, and then it will be easy to show you the final result. So the idea is that supposing I have a CFT V and another CFT V prime, whose characters have mutually conjugate modular representations rho and rho prime. Then such a relation, the rho transformation of the first one and the rho prime of the second one will cancel. Basically, rho prime is rho dagger. Okay, and then such a sum will be modular invariant. So this is called a gluing relation, and this is a necessary condition for a coset relation to hold. That I already said. The question is whether this condition is also sufficient. That is, if this holds, then a coset relation holds. And here we have to appeal, di are some integers, which basically take into account, again, in our case, I think there are no di's. I put in di's into this slide this morning, but I realize now that all di's are 1 for two primary case. They arise exactly when there are multiple primaries for the same character. So probably for this talk, they shouldn't be there. It's a more general version of the relation. Yeah, so do all V prime that transform in the conjugate representation rho prime arise as cosets in this way? If that's true, then the theorem I quoted is true, and we are done. So now we use the fact that a CFT is associated to a modular tensor category. And this object is basically the topological information of a CFT, which is the modular representation rho, which I've discussed. Also the braiding and fusing matrices B and F introduced by Moore and Seiberg. Also the central charge mod 8 and a few other basic data. And basically they capture the data of a topological field theory, which comes from the boundary of a Chern-Simons theory with of a particular kind. And the map from CFT to modular tensor category is many to 1. So there are many CFTs for any given MTC. However, and now the rank of an MTC is the number of primaries, not characters, but primaries of the associated CFT. And this is why we had to restrict to fixed number of primaries. Now, it turns out that if the MTC for two different CFTs are mutually conjugate, that means the actual MTCs are conjugate as MTCs. Now, there's a well-defined concept of conjugation for MTCs. which is that when you pair the MTCs, you get a trivial MTC. That's when you say one is conjugate to the other. If the MTCs for these two theories, V and V prime, are conjugate, then it follows that the bilinear relation I wrote is a relation between CFTs and not just characters. So this is the key thing that we want to lean on. And I don't have a very easy explanation for this fact, but basically MTC data is supposed to uniquely determine enough properties of the CFT that a CFT actually exists. So in rank 2 and also 3, there's a theorem that the modular tensor category for a CFT is uniquely specified by its modular representation. That means only by the S and T matrices, or by what I called rho, namely the way the characters transform. We don't need to look at braiding and fusing, because those, once you know, there are only a few modular tensor categories of rank 2. In fact, there are only 2, so-called Semyon and Fibonacci. And it turns out that the MMS theories that I listed are respectively matched to Semyon, Fibonacci, Fibonacci bar, and Semyon bar, bar being the conjugate MTC. And also for rank 2, the possible modular representations are known. And in fact, one finds that all possible modular representations for two primaries are obtained from those of the MMS set by either complex conjugation or multiplying by a phase. You can understand readily why the phase comes in, because meromorphic theories themselves have a phase. So when two characters pair up in a bilinear relation to be a meromorphic character, like here, this right side could be j to the 1/3. In that case, one is not really conjugate to the other, but conjugate to the other times a phase, so that this one can transform by a phase. That's something you can easily take into account. That's sort of trivial. And then the result follows that all CFT with exactly two primaries are cosets of a meromorphic theory by a member of the MMS set, which are 4 theories. So this is the theorem. And now we can classify all unitary two primary RCFTs with any central charge by enumerating all cosets. But as we'll see, it stops at 25, actually strictly less than 25. So a couple of things to be said, and then we are basically done. First, the Riemann-Roch theorem, remember that, this is a theorem in general, but now it would be nice to know what are the, it's not really necessary, but it's nice to know what are the L values we should expect. So unitarity says that H is positive, so L is bounded above by C over 2 plus 1. And since we have picked C less than 25, L is going to be less than or equal to 12. And so the possible values are 0, 2, 4, 6, 8, 10, and 12. Now we've already done, and out of these, it turns out that there are no admissible characters having C less than 25 and these values of L. This is something we showed separately in 2018. So if there are no admissible characters, there's no CFT, so you don't have to look for it. That leaves the possible values 0, 2, 4, and 8, of which 0, 2, and 4 we have just classified. We didn't show it's complete yet, but in a minute we'll say that that's complete, and it only leaves L equals 8 to be classified. So yeah. No. L has not been studied up to 12 actually. I'll keep it a mystery for one more slide. It will come in a minute. So, but some of these statements are true more generally, but okay, right now, so this is something we can say from this paper, that if L is 0, 2, or 4 mod 6, then the modular representation or the theory must be of this form, or a coset of C equals 24 by this set, or a coset of C equals 16 by this set. And we've already found 0, 2, and 4. We have to find 8, and it will lie in the middle set, middle category. It will be a coset of C equals 24 by these, but a different kind of coset. Now let's come to C less than 25. By restricting C less than 25, I've restricted that the meromorphic theory should have central charge less than or equal to 24, and we only make use of 16 and 24. If I allowed C equals 25, I would need to include, for example, the quotient of a C equals 32 meromorphic CFT by E7. That would have central charge 25. But we saw in the beginning that C equals 32 meromorphic CFTs are unclassified and probably unclassifiable. If that is so, then we can't know all quotients of C equals 32 theories by E7-1. So we can't find all theories at C equals 25, and that's why we put the bound below, just below 25. No. No, so the lucky thing is that between 24 and 25 there isn't anything. So we could have said less than or equal to 24, but we were able to push it to less than 25 because there aren't any admissible characters in that range. Admissible characters for this case are classified, and there are none with central charge between 24 and 25 for two primaries. So therefore, you can be up to 25, you can go, but strictly below. If you go to 25, this case obviously is a class, right? I mean, these are obviously there. But the point is we can't classify this subcase, so we can't classify everything. Now, actually, it might be possible to classify meromorphic theories at central charge 32, which contain an E7-1 factor. Because I can discuss this privately later, but it's by classifying admissible characters. So it follows in particular from this paper, also from the work of Mason earlier classifying the. No, it's not very parameters. It's the, well, this is this paper gave a classification of all admissible two character sets. So you can, the list of central charges allowed, it's infinite, but you know the list. It's basically a repeating list. It's of the form 1, there's one family which has 1, 7, 13 and so on, and another family like that, and so on. There are 4 families, and it's none of them has between 24 and 25. Okay, so this right away confirms that whatever we did for 0, 2, and 4, which I went through with you in detail, is complete. So we don't need to worry about anything more existing at L equals 0, 2, and 4, which fits with the fact that these MLDs could be solved, and anyway, that was the number of admissible characters. There weren't any more, so it matches well. But L equals 8 is a problematic case because as soon as L crosses 6, you start to find MLDs which have free parameters. And so it's not possible to restrict to a finite set of admissible. There are admissible characters, they are known, but they are not a finite set, they are an infinite set. But we find from the Wronskian index that to get L equals 8, you must take a non-trivial embedding of a Kac-Moody algebra in a numerator factor of a Shelikin's theory. This is the only way to get L equals 8. And this is a non-trivial embedding is different from the kind of trivial embeddings I discussed where you just delete the factor in the numerator and you get your answer. So this is a non-trivial embedding. And so it follows that at C less than 25, every two primary CFT with L equals 8 is a coset of a Shelikin's theory by one of these 4 embedded properly inside a simple factor. And that now reduces it to, and the central charges you get are again 24 minus these. So the list is the same, but the conformal dimensions are different because L is 8 and not 2. And then one computes all possible such embeddings. It's very complicated exercise involving Dynkin and embedding indices. And we found 98 theories. Well, just to give you an example, if you take this Shelikin's theory, which we've seen a few times, then A11 can go into A31, but it could also go into G21. It can't go into D73 because of some rule about the level of this 1 versus 3. Because the embedding algebra has to have a higher or equal level as the numerator. Okay, so let me just flash for you the results. I'll skip over all this for lack of time. And also the subtleties, which I definitely don't need to show you. But anyway, this is just, I don't expect you to be able to read this. But this is a list of theories 1 to 82 and 83 to 123. But to be a little more useful, I've blown up a small segment of it. And this gives you some idea what's going on. So this is the L value, which is 2 for these two and 8 for the others. In each case, you have a Shelikin's theory. So S of something is the Shelikin's theory with that Kac-Moody algebra. The slash on the right side tells you what we are embedding, and here it tells you what we are embedding it into if the embedding is ambiguous. For example, G21 goes into G21 means we are deleting this G21 and not trying to embed G2 into the other factors. And these two embeddings are trivial. In other words, G21 cancels this, and here G21 cancels one of these three factors. But here G21 is going into B31. Here G21 is again going into B31 and so on. And these have non-trivial commitants. And what you see is that in most cases, but not all, the non-trivial committant pulls out some, gives you some minimal model. We find not just L7/10, but also L half, which is the icing module. We also find the Potts case, L4/5. So 3 of those. So this is just a blow up of a segment of our classification, and just to show you how it works and how the answer looks. So in summary, this is a complete classification of all CFTs with C less than 25 and exactly 1 non-trivial primary and 1 trivial primary. Last, this is the degeneracy of the non-identity primary. And it's an interesting fact that it comes out huge in some of the cases. In fact, the referee whose report we got day before yesterday asked us to explain why it's like this. And you know, for years we have known that it's like this. I mean, all my previous work we have seen this, but really we don't have a good explanation. It's quite intriguing. Yeah.
Last number is the representation of the 0 port.
Exactly right. And probably what it means, you see, in these cases, because there's a minimal module that never has any degeneracy, so it's not contributing. And this 1 means that probably the, I don't know what it actually means. It means that somehow A4 and A9 have representations which are the 4 and 9, they're fundamental representations, but neither of those can occur. So I'm actually not even sure how this can be 1. Yeah, but okay, so that means the non-trivial primary is a singlet, but I thought that's the identity normally. So why should?
But it could be the excited person of the ports.
Yeah, that could be. That could be. So that's right. That's right. So it must be that this is an excited state of the pots, or a non-trivial primary of the pots rather, of the tricritical icing, coupled with trivial with the vacuum of these. Yes, yes, yes. That's what it must be.
Correspond to some combination of your maps.
Yes, 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 absolutely. Yeah, yeah. I think for some examples, we have. It's not very hard. If you look for the prime factorization of 15847, there are not many available ingredients here. Only if you see E6 and E7 are at level 3. So we'll have at least 2 or 3 or 4 non-trivial representations of those, and those will definitely divide this number. In any individual case, you can easily see what's happening. Yeah.
And this will be a single irreducible representation of that algebra.
Of the extended chiral algebra. Yes.
Extended is not extended chiral algebra, of course, but just the current algebra.
In this case, there is only a current algebra. So this will be some, I think, okay, whether it's a single irreducible represent, I think so. I think I've done a few examples. Not completely sure. Can look at it. Okay. Yeah, that's actually follows more or less. Yeah, they are same, even though they come from different algebras. And that's, I think, somehow related to the fact that these characters are rigid. This L equals to, they are isospectral. These two have the same spectrum. So I think just modular invariance says that the numbers would be the same. If you look at the larger list, you see that the last column is always a smallish number. But here there are 3, 2, 3, 8, 4, many of these. So yeah, it is something which would be nice to understand. Now I'm puzzled because I'm not finding the examples I just showed you. Oh, in this column probably, yeah. These are the ones I think these I showed you. Yeah, okay. Conclusions. So one obvious thing is to extend this to more than 2 primaries. So in 1989, we started to study the 3 character case and did quite a lot actually. Revisited in 2015, revisited again in this paper. These people looked at it. I revisited again with some other students. And each time we found something more. But last year, 3 independent groups, one of which is Chethan, Gowdigere at IISER, with his student Jagannath at also IISER, and Arpit Das is at Durham. And these two other groups independently and around within a space of couple of weeks completed the classification of admissible characters, but for L equals 0. Now we are not talking arbitrary L. And in this paper, which we completed a month ago, we were finally able to, from this set, identify all the cases which are actual CFT, and we use the same gluing and coset relations to identify that. And so there's a complete classification of 3-character CFT, and now it's characters, not primaries. But honestly, it's at a slightly lower level of mathematical rigor. So I think here we might, some of our 3-character CFT might have so many primaries that the uniqueness of the MTC cannot be guaranteed. So it's modulo some assumptions. And these are some of the theories in our list. You see again, these are 3-character extensions of Kac-Moody algebras, and once in a while some minimal model might show up. Okay. It may be possible to find a complete set of meromorphic theories at central charge 32 having an E71 factor. So that's something I'd like to look at. Harvey and Wu had a different approach to finding admissible characters using Hecke operators. It's not clear how this relates to that, but should do so. My collaborator, Brandon Rayhaun, has also worked on penumbral moonshine, and there's a relation between the kind of VVMFs we found and certain types of finite groups. So these are some interesting open problems, and with that I'll stop. Sorry for going over time. Yeah.
Thank you, Sunil. Are there more questions?
Yeah. Yeah, but actually you can do the reverse also. The point is that if I multiply the whole MLDE by some power of eta, I'll get an MLDE with positive weight. So if I have an MLDE for forms with positive weight, I can divide by powers of eta and get something which has 0 weight. And people use that. But of course, if you divide and multiply, you will affect the value of L and so on. So you have to be a little careful. Yeah.
Did you have any theory in the list which had just pure Virasoro and
So in our list with 2 primaries, there wasn't any such theory. Once you go to 3 primaries, there's a famous. No, so here we were restricting to unitary also. In our work, we found the Yang-Lee theory, which is non-unitary. But in this work, we restricted to unitary. But at 3 primaries, you find a theory called the baby monster, which is the quotient of the monster by the Ising model. And that's very pretty because both the monster and the Ising model have no Kac-Moody symmetry. And so their quotient also doesn't. And that's just very nice. So that's a way of getting, so the baby monster is a good example. And mathematicians have given a name to it. So theories of type OZ, I forget what OZ means. I think O is 0 and Z is something. Those theories whose weight 1 space is empty, which means their spin 1 currents there aren't any. And that's interesting because, right, we saw that in all the examples we look at, the spin 1 currents, the Kac-Moody things dominate. But we really would like to understand CFTs without Kac-Moody currents, because that will teach us more about the higher spin structure, which is clearly important.
Just to understand, so you're saying baby monster CFT is an example of a unitary CFT, which is rational, but only has Virasoro algebra.
Yes, yes. But it has infinitely many Virasoro primaries, but it has only 3 generalized primaries, generalized under its full chiral algebra, which is not just the Virasoro algebra, but it has many other spin 2 generators, which in that theory are primitive. I mean, they are independent. So that's, yeah, okay. Sorry, so I think I should have not said just Virasoro. Yes, you're right. In fact, it can't be, right? If it's rational and has C greater than 1, it can't be just Virasoro. So I said that too fast. It has no Kac-Moody symmetry, but it has actually it has no, some, not 196,884, but some large number of spin 2 currents. Whatever is the commutant of the Ising stress tensor in the spin 2 currents of the monster CFT.
characters and don't be Virasoro. He's probably the young.
That's correct. That's correct. That's absolutely correct. I mean, that's because anything with only Virasoro and rational is classified and has C less than 1. Higher speed, yeah, in a way, yes, because baby monster is such an example. It's a CFT with a large number of spin 2 fields in the chiral algebra. Now, my point is, all the theories I've discussed also have a large number of spin 2 fields, but they are bilinears of the Kac-Moody currents. So we don't think of them as new. Now, if we find a theory which has no Kac-Moody current, then the spin 2 fields can't be bilinears of them since they are not there. So they are independent. And this is how CFTs work. The higher spin fields would like to be bilinears of or multilinears of lower spin fields. Unless there aren't any lower spin fields, then there may be new independent higher spin fields.
So what is the simplest higher spin theory that time?
The monster. It's a meromorphic theory with no Kac-Moody algebra, and it has 196884 spin 2 fields. Yeah, of which one of those 196884 is the stress tensor, and 196883 are spin 2 fields that form what is called the Grice algebra. So they have a particular commutator algebra between them called the Grice algebra. Yeah, so if you want to you can't get rid of all spin 2 because Virasoro has to be there. So I don't know any rational CFT. So this is a good question. Any rational CFT with any number of characters which has no Kac-Moody and also only the Virasoro at spin 2 and starts having chiral algebra from spin 3. That's the question I think you're asking. And it's a lovely question, and I don't know right away. I don't know the answer for sure, and I'm sure it's not known. But I think these techniques are there and it's worth looking at. It might need one more clever idea added to all these techniques, but a lot of techniques are there. Well, the problem is that people look at W algebra representations, but then, yeah, maybe they even do. No, there are W minimal models, and the best way to understand them is as cosets. So if you look at the cosets which I was showing you earlier, which were this type. Where is it? Sorry. Okay, I'll not be able to find it now, I think. Let me try once more. Yeah, so this coset has A1 comma K cross A1 comma 1 over A1 K plus 1. If I generalize to AN comma K cross AN comma 1 over AN K plus 1, I get the WN minimal models. So those are known. So now I'm not 100% sure, but it could be, and you can see why, because here you see there's a Kac-Moody algebra in numerator and denominator, but somehow the denominator manages to destroy nothing in the numerator commutes with it, and that's how we get minimal models. So I think the W minimal models are of that kind. I didn't think of it this way, but maybe those are the examples.
What is the lowest number of characters one can get?
Yeah, I think 6 or something. I think the 4/5, which is a 3-state POTS, is the bottom of the W3 minimal models. Central charge 4/5. Is that true? 10, I think.
10 characters in the
10 primaries. Yeah. The W might have less. I think it's yeah, that has less. That has less. I don't remember the number, but it's easy to find.
What about that number was find it in the classification?
Sure. Sure, of course. But then what's the point of finding it? Only if.
One example where it arises, then one can track.
Yeah, that might be a good idea to first find it in the MLD formalism or coset formalism, and then try to see if there are more of such things around. Yes, I agree with that. Yeah, for example, there might be extensions of W algebras. Like You might have some W3 module and a W4 module and a W7 module all multiplied, and it might be that there's a 1 character extension of it or 2 character. Yeah. The question? Yeah.
Are there any questions from the virtual audience?
Sorry. I don't know if the virtual audience is still alive.
May I, Sunil? Can you hear me?
Yes, I can.
Yeah. Very nice talk. Thank you.
Thanks.
I have a naive question. You get these factors, this Ising model and tricritical Ising model. As Virasoro theories, they have more than 2 primaries, right?
Yes.
So how do they, in this case, how do they combine?
Yeah. So what actually happens, let's see. Just let's take one example from that blown up table. So in this table, let's look at the 3rd line. So there's an L7/10. Now 7/10 is tricritical Ising and it has 6 characters. But now you have to multiply out all the characters of everybody. So now you'll get a few hundred or maybe a few thousand of them. But some of them will have integer conformal dimension because of some coincidence that the dimension of the tricritical Ising primaries matches the dimension of these up to mod integers. So then in this product, you'll get some integral dimension primaries. And then those will be added back to the identity character to make the meromorphic theory. So it uses some aspects of the tricritical Ising module, but it's not the modular invariant of the tricritical Ising module. It's a completely different modular invariant, which exists only because you have multiplied tricritical Ising with bunch of other stuff. So one very broad lesson from this talk and this work probably is that just because you know a lot about individual simple Kac-Moody algebras, you really don't know much about what kind of interesting CFTs come about when you multiply them. I mean, from a priori considerations, nobody would think of multiplying D6, 2 with C4, 1 with B3, 1 and L7, 10, and then say, let's see if on the off chance there are some 2 character theories for that. But the coset construction just gives you the theory right away.
Yeah, thank you.
Any last questions for Sunil? I see nobody. Thank you, Sunil, for your nice talk.
Thank you.